that every bounded monotone sequence has a limit. So, and of course you can combine the two things to prove something called the Bolzano-Weierstrass theorem. So every bounded sequence has a convergent subsequence. How so? So if you have a bounded sequence, right? If you have a bounded sequence, then, well, first of all, being a sequence, right, it will have a monotone subsequence. And this monotone subsequence will be bounded as the subsequence of a bounded sequence. So, right? So by the first theorem, a bounded sequence will have a bounded monotone subsequence. But a bounded monotone subsequence will be one of the objects that must have a limit by the second theorem. Okay? So and the proof was, so Xn as a monotone subsequence Xnk. But then Xn bounded trivially implies that every subsequence is bounded, right? So in particular Xnk will be bounded. So that Xnk will be bounded and monotone and thus convergent. So for example, remember sign of n, right? This does not converge, but it is bounded, definitely. So it has at least one convergent subsequence. So remember sign of n, right? It was like I had the sine function, right? Which has a lot of beautiful symmetries but all the symmetries and nice behaviors of the sine function are somehow related to the number pi, right? And pi has nothing to do with the sequence of natural numbers 1, 2, 3, 4, 5, right? It's completely unrelated. So here you see how things in mathematics can quickly spin into a mess, because here you have these natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and there is just no relation between them and the values, simple values taken by the sine function. So we use these to show that this guy has no limit, right? Because it takes infinitely many times values larger than 1/2, and it takes infinitely many times values less than -1/2. So this shows that no subsequence can converge. Okay? So sorry, that the sequence has no limit. But the Bolzano-Weierstrass theorem tells you that there must be at least one convergent subsequence. Can you imagine that? I cannot very well, because I know that, for example, in each of these intervals, right? Remember these intervals where the sign was more than 1/2? I know that in each of these intervals, it folds at least one natural number, right? So I will compute the sign there, and it will be a number between 1/2 and 1. Right? But who knows how much? I mean, I don't know. It's a sine of n equal to something between 1/2 and 1. So this theorem is telling me that if I consider those guys, there will be a way of selecting them so that they go somewhere. You see, this gives you no idea of how to compute this limit. Huh? And actually, I have no idea of the answer. So what are the possible limits of subsequences taken out sine of n? I have no idea of what the answer is. So it seems to me kind of a delicate question. Because it's really about, in a sense, it's really about what are the possible limit points if you start spinning around the circle, right? And you take 1, 2, 3, 4, 5. So you take natural number distances on the unit circle, and I'm asking you essentially where you can stop with this process. What could be the accumulation process points of these things? This for me is an open question. I've never heard the answer to it. So that's like saying, just telling you how fast things can get extremely complicated, okay, with very few ingredients. Okay, so now, well, this was just to recap what we did last time, right? Well, last time, actually, what we did last time, the main thing we did was constructing a sequence which has no limit, but for every real number, our sequence had a subsequence converging there, right? So that's a very important example that you should study. So we also made an example, so we constructed a sequence xn such that for every real number L, there exists a suitable subsequence of our xn such that the limit as k goes to infinity of x and k is equal to L, right? That's also something we did. So which also tells you how complicated can be the notion of sequence, right? Because I think one initially doesn't have this perception of sequences being that nasty, right? Because you think of 1 over n, 2 to the n, I mean minus 1 to the n. It's like kind of pretty simple objects. That are the sequences you see in calculus, right? That's the complexity you see. I mean, it's objects of which you can compute the limit. That's it. Either they go to plus infinity, or they oscillate, or they go somewhere. But actually, when you talk about sequences, what you're really talking about is objects as complicated as that one way. The huge table we wrote last time, okay? Along the columns, we were constantly equal to a rational number, and then jumping along the columns, you were able to converge to any real number. Okay. So now that you start appreciating the complexity of the thing, I ask you a question. So think about the definition of limit. The definition of limit tells you that the limit of the sequence is a given number, provided you can show that for every epsilon, you are ultimately close to that number, right? That's how it works. But now, what is the main ingredient to check that a number is the limit of the sequence? Is guessing the right number. So I have to start running this test of being epsilon close ultimately, right? So, and that's a bit of the difficulty of using this definition. So, because in a lot of cases, you don't know what the limit is. You don't really have just a vague idea of what it could be, but you don't know if beforehand what the limit could be. So, somehow one needs a criterion to say that the sequence is a limit without guessing what the limit could be. Okay? So, now I'm going to show you a criterion to say that a limit exists without knowing what it could be. And now that you have started appreciating the complexity of the matter, you should have a guess about such a tool could be useful, right? Yeah.
Don't we know that if it's bounded in monotone?
Yeah.
That's the only criterion that you have, right? So far.
Right.
So the bounded and monotone sequence theorem tells you that every bounded monotone has a limit. It's such a criterion. But it has a bit of a defect, right? It applies only to monotone sequences. right? I mean, monotone sequences, it's clear that they're special because they're very simple. But take something like sine of n or something really complex. Monotonicity is not something you can expect in life, right? So it's good to have the bounded monotone theorem, but that's not enough. So you need something more precise, and that's what comes next. So there is a definition. So we say that xn is a Cauchy sequence so the name comes from the French mathematician Cauchy, who was the person that first put this idea at focus. So a sequence is a Cauchy sequence if, for every positive number, there exists a threshold n such that, sorry, an epsilon, let's call it, such that xn minus xm is less than epsilon for every n and m greater or equal than n epsilon. Okay, so if you want, that's very similar to the definition of limit, right? That's very similar to the definition of limit. The definition of limit would be for every epsilon positive, there exists a threshold at epsilon, such that xn minus the limit is less than epsilon for every n larger than an epsilon. Here it's different. I'm not putting the limit here. I'm comparing xn with every subsequent value of the sequence. They're both larger than this, right? So every subsequent value. So let me reformulate. This is how you're going to find it in the book. Let me reformulate this idea, introducing some terminology that is not in the book. So, given a sequence, let me call its oscillation after n, so omega n will be the supremum over xn minus xm among all indices that are larger than n.
Did you say that xn was the subsequence of n?
No, that was no subsequences here. You just have a regular
Okay, it's
sequence.
just a regular range.
We have a sequence, you're computing it at different indexes, but there are no subsequences at the moment.
Okay.
So let's put a moment on hold this definition, okay? Let me try to explain it to you from another point of view. Let's call the oscillation of our sequence the largest, the supremum of this set of real numbers. So I take the index n, okay, and I compute the difference between the value xn and the value xm for every subsequent m, okay? Do you see what's the idea? It's like, well, I have my sequence, I choose xn, and then I compute the largest difference between xn and all the subsequent values, right? So, and I call it the oscillation. So let's try to draw a picture, right? It's like, say this is the value xn, and I am looking at my sequence at n, okay? Then I start considering n plus 1, say it's here, n plus 2, it's there, some larger value of m, and so on, right? So for each of them, you can compute the absolute value of the difference, right? For example, this height here will be xn minus xn plus 1 modulus, right? These, okay, here let's put it like that. These could be xn minus xm modulus. So it's like I look at my sequence from xn, and then I measure the oscillation after the value n. You see? You see it better now? So I got to understand, given that I am xn, how much my sequence is opening after that. And I want the largest possible opening. Okay? That's the oscillation. That's why it's called oscillation. Because you really measure how far you oscillate with respect to the value xn. After that, not before. Before you care anything, as you know, right? I mean, it's just what happens at infinity that bothers you. So that's the oscillation. And another way to reformulate being a Cauchy sequence is that the oscillation goes to 0. So xn is a Cauchy sequence if the limit as n goes to infinity of the oscillation omega n is equal to 0. Okay? You see it better now? And that's exactly what's written here if you think about it, right? Because when I ask that xn minus xm is less than epsilon, for every n and m larger than an epsilon, okay? In particular, I'm telling you that omega of an epsilon, so the oscillation at an epsilon, it's less than epsilon. So this block here, this block here implies, and is actually equivalent, in saying that omega of an epsilon is less than epsilon. Sorry, that omega n is less than epsilon for every n larger than an epsilon, right? Because fix n larger than an epsilon, then have m range among those ones that are larger than n, get them in particular, and then you get that the supremum over m larger than n is less than epsilon. So this means that omega n is less than epsilon. When? For every n larger than an epsilon.
Doesn't this mean that all xm will be the limit of xn?
No, because xm is not a fixed number. And you see, I mean, xm is not a limit, right? Because you have to move it in the definition. You cannot keep it fixed. The next try, I try a different epsilon. I will have to increase an epsilon, and so I will have to restrict the range of the numbers I'm considering. So when you compute that something is a limit, whatever you put here must be independent of epsilon, otherwise it will be not. You are cheating.
This has nothing to do with subsequences.
Not yet.
Not yet.
It will soon end up there.
Okay.
Okay? But for the moment, I'm just telling you, right, that so theorem, if you are a Cauchy sequence, actually if and only if the oscillation goes to 0. I will leave this for you as an exercise, okay? I'm not interested at this point in showing this in detail, but it's a triviality. I mean, you should be really able to do that. So proof, easy. So for me, it's just for the purpose of this lecture, I would like you to understand the condition as saying that the oscillation goes to 0. Okay? Does it make sense? The idea of the oscillation going to 0. So it's like at each point on my sequence, I just look what happens after. So for example, take the sequence xn equal to -1 to the n. What is omega n? How much? What's the value? Even worse, 2. Right? Because, so this is going to be 2 for every n. Because for this sequence, say this is n, and n was even, right? So xn was equal to 1. Then my sequence is just oscillating, right? -1, 1, -1, 1. So the supremum, on this point, the oscillation is 0. But on this other point, the oscillation is 1 minus -1. So the supremum of the oscillation is always 2. Okay? So -1 to the n is definitely not a Cauchy sequence. Yeah, you have a question? No, here we go.
Me?
Yeah,
Oh.
no question. So, let's see, I don't know, for example, let's do an easy one. Say that xn is increasing and bounded with L given with L being equal to the supremum of xn. So you call the supremum like that. Then my claim for you is that omega n is just going to be L minus xn, right? Because say that you have this sequence, so on. it's increasing, right? So the values are increasing, but it's bounded, so we are converging to some limit, L. So I look at here, this xn, and I want to compute the maximal oscillation between xn and the subsequent values of the sequence, right? So for example, if this is m, this will be xn minus xn modulus, right? It's clear that the oscillation of an increasing sequence at step n is just the supremum minus the value of the sequence, which you achieve as essentially as n goes to infinity. Yeah.
So, for now, this claim is not stronger than the previous one we had, the bounded n.
No, I'm adding nothing for the moment. I'm adding nothing. I'm just telling you how to see this oscillation on previous examples.
Okay.
All right? Yeah.
Is there a relationship between the Cauchy sequence and the sine function example that you showed us a few weeks ago?
Example, what is the oscillation of the sine function, right? Okay, that's hard. It's hard to understand it, right? It's quite clear, for example, it's quite clear that the oscillation cannot go to zero, right? I don't want to write this into much detail. Let me just answer you with a picture, okay? So why in that case the oscillation is not going to zero? Because you had all these peaks, right? Where you were taking at least the value 1/2. But then you had a lot of other peaks where you were at least taking the value minus 1/2, right? So you see, if I pick some n here, which sine of n is larger than 1/2, then the oscillation will be at least 1, right? Because I certainly can find some m where sine of n is less than minus 1/2. Well, at this point, sine of n was at least 1/2. So the oscillation is at least 1 at each of these points. And since you have infinitely many points where the oscillation is at least 1, so for sine of n, then omega n is going to be at least 1 whenever sine of n is larger than 1/2, say. And since you have infinitely many of these n, right, because you take at least the value 1/2 infinitely many times, the oscillation cannot possibly go to 0, because it will be at least 1/2 infinitely many times, okay? So you see, you start seeing a pattern, I think. On sequences that we know they are not converging, the oscillation doesn't go to 0. Sequences that we know they are converging, like bounded monotone, the oscillation goes to 0. Now, Cauchy criterion is, the Cauchy definition is, a sequence is Cauchy if the oscillation goes to 0. Now, what will be the theorem? The theorem will be that a sequence is convergent if and only if it's Cauchy. So, if and only if its oscillation goes to 0. That's what we are going to prove now. So, really looking at the oscillation, it's another way to formulate the idea of being convergent. But what is the cool thing? The cool thing is that to check if the oscillation goes to 0, so to check if I am Cauchy, I don't need to guess the limit. You see, in the definition of the oscillation, there is no limit mentioned, ever. It's just the values of the sequence, okay? So this is the big advantage of working with this idea of Cauchy sequence. So let me state the theorem and prove it, okay? So the theorem I want to prove now is the famous Cauchy criterion, telling you that, so theorem, xn has a limit if and only if xn is a Cauchy sequence. Which is really an extension of the bounded monotone theorem, right? Because we have just checked that, say, every bounded increasing sequence is Cauchy, right? So the theorem was just an example of this theorem. And every bounded monotone sequence is Cauchy, so it's really just a particular case of what I'm going to prove now. Okay, so of course, course, the most interesting implication is when you prove that if you are Cauchy, then you converge, right? But let me first check that if you have a limit, you're Cauchy. So let me first prove this. To prove, we first do this implication, okay? So I want to show that if the limit, if there exists L such that the limit as n goes to infinity of xn is equal to L, then the oscillation of your sequence is actually going to 0, right? That's the first implication. Convergent implies Cauchy, all right? I want to show that if we have a limit, then we are Cauchy. Okay, think about the statement. I know I have a limit, right? So you know that for every epsilon, I know that if this is my limit, I know that for every epsilon, I will ultimately take values inside this interval. Right? That's what it means having a limit. Given epsilon, I will ultimately be in that interval. Now, what is, so pick now any two values, n and m, which are inside this, above the threshold, so they are inside the interval. What is the distance of xn and xn? At most 2 epsilon, right? So this means that for every couple of value after n of epsilon, the distance will be at most 2 epsilon. So what happens to the oscillation? It's going to 0. And you are Cauchy. So that's the proof of this implication. Let's write it down formally. Okay? So by definition of limit, for every epsilon positive, there exists a threshold such that xn minus L is less than epsilon over 2 for every n larger than n epsilon. Then, if now I pick two indexes, n and m, both larger than an epsilon, I find what? I find that xn minus xm, by triangular inequality, I can compute this as the distance of xn from L plus the distance of xn from L. And since individually each of them is less than epsilon over 2, their sum is less than epsilon, right? So this guy is less than epsilon over 2, and this guy is less than epsilon halves 2, so what I get is less than epsilon. So I have proved that I am a Cauchy sequence, right? Because I have shown that ultimately the oscillation becomes smaller than epsilon for every epsilon possible. So I am Cauchy. Okay? Are we good here? So that's one implication which is non-interesting one, it's easy. Actually, the interesting one is the opposite, right? It's having a criterion to accept that something is a limit. So, now let's prove the other implication. So we start from the Cauchy sequence, and so we want to show that the sequence has a limit. All right? Okay, so step 1, we show that xn Cauchy implies xn bounded. After all, we know that if a sequence is converging, then it's bounded, right? We know that. So, kind of a baby steps, okay? So, you want to prove that you're convergent, we prove at least that you're bounded, which is a starting point, right? Okay, why do you expect the sequence to be bounded? Think about it. The oscillation is going to 0, right? In particular, it means that after a while, the oscillation is going to be less than 1. Say. So there will be some xn, such that after that I oscillate at most 1. Okay, so this implies that all the values after xn will be of xn of 1, up or down. So they're all bounded in terms of xn. What's left outside? Finitely many values that I had before, which are harmless, right, as boundedness is concerned. That's why I'm bounded. Okay, so the idea is that, the idea to show this is that since omega n goes to 0, that's the definition of Cauchy, since omega n goes to 0, xn minus xm, well, it's easier, I mean, it's faster to write it down formally than to explain again the idea in words. I should have done it, it's really easy. So, so the fact that, indeed, the fact that the oscillation is going to 0, right, tells me that there must exist some threshold such that omega n is less than 1 for every n larger than n naught. That's the oscillation going to 0, right? So in particular, omega n naught, which is the supremum of xn minus xn, so x naught minus xn for n larger than n naught, in particular, this guy is less than 1. So the oscillation measured from n naught on is less than 1. Okay? So this is a fancy way to write down just xn naught minus xn less than 1 for every n larger than n naught, which in turn implies that the modulus of xn is less than the modulus of xn naught plus the modulus of xn minus xn naught. These are all the formal steps, okay? Which is less than x of n naught plus 1. So hence, what you find is that xn, in general, for every natural number n, xn is going to be less than the maximum between x1 modulus, x2 modulus, x n naught minus 1, and then you have x naught modulus plus 1. Because you have the first couple of billions of terms up to n naught minus 1, and then counting from n naught on, we are always below the modulus of x of f naught. So you're sure that the sequence is trapped between these values. All right? Do you have questions on this step?
Why is omega n less than or equals to 1?
Because I know that the limit is 0, so I apply the definition of limit with epsilon equal to 1. Kind of using, I'm not even using all I know. I know it's going to 0 oscillation, right? But I don't want to use that much yet. Okay, now there is step 2, where we show that the limit exists. Okay, how does it go now, the conclusion of the proof? So step 2. To complete the proof. So we have seen that xn being Cauchy implies that xn is bounded. Alright? But now being bounded by the Bolzano-Weierstrass theorem implies the existence of a subsequence such that subsequence converge to some limit f, right? So somehow I have managed to show that my sequence had a converging subsequence. simply because being Cauchy implying being bounded, all right? And now we have to just to get this idea. So what does it mean to be Cauchy? Again. So are we good up there? Cauchy implies bounded, this was step one. Now that you have a bounded sequence, at least you know there is a converging subsequence. Which is the case for sine of n, right? Which is not convergent. Sine of n has bounded subsequences. So far we don't see this limit coming out of the proof. But now we are really using the assumption that the oscillation is going to 0 in a crucial way. Why so? Because in general, think about this, in general, the fact that I have a subsequence converging doesn't imply anything about the sequence, right? We've seen that you can have subsequences converging to every real number, and so on. So this alone doesn't imply anything. But I also know that the oscillation is going to 0. So take the limit L of your subsequence, okay? And you know that your subsequence is going to be nearby there with an error epsilon. All the terms of your subsequence. Now pick just one term of your subsequence. What is the oscillation of the original sequence after that term? Well, it can be made small, right? You see that? So, since the subsequence is converging, I can put some x of n 50 epsilon close to the limit, right? But then how much I oscillate after that value? As small as I wish. I mean, it's just maybe I have to pick not x and 50, but a larger value of the subsequence, a larger index. But definitely the oscillation will be small. So it's like once the oscillation is small, the fact that you have the subsequence converging somewhere, then the subsequence hooks the rest of the sequence, and it forces to converge to its limit. It kind of traps it with itself. Okay? So the subsequence converging is forcing everything to follow it. So that's the idea, because the oscillation is going to 0. So now we're going to check that this guy is somehow trapping all the sequence with itself because of the Cauchy problem. So formally, this is the argument, okay? So formally, let me do this. So these, let me call this star, the fact that I converge to limit, right? So fix epsilon positive. Star says that there exists some integer k epsilon such that x and k minus L is less than epsilon for every k larger than k epsilon, right? That's one thing. That's the fact that my subsequence is convergent. All right? While Cauchy tells me that there exists some threshold such that xn minus xm is less than epsilon, provided both n and m are larger than an epsilon. Okay? Now remember what you know about these indexes nk, right? They were a strictly increasing sequence of natural numbers, right? So recall that nk are natural numbers with nk strictly less than nk plus 1, right? So, and a strictly increasing sequence of natural numbers is always able to be larger than whatever you want, right? So, definitely there exists some, I don't know, k bar of epsilon, such that n of k bar epsilon, sorry, n of k, such that, sorry, n epsilon is less than n of k bar of epsilon. At a certain point, the indexes of my subsequence will be, they become larger and larger, right? Because that's a subsequence. They will be large enough to be above the threshold and epsilon, okay? So So now you put everything together. And you notice that if k is larger than the maximum of k epsilon and k epsilon bar, then you have two things. So you have that x of nk minus L is less than epsilon, and you have that nk is larger than an epsilon. So that x of nk minus xm is less than epsilon for every m larger than an epsilon. So because if you pick k larger than k epsilon, x of nk is epsilon close to L. This was the convergence of x and k to L. But if you pick k larger than k bar, then nk is going to be larger than nk bar, which was larger than an epsilon, right? So that I can plug in nk and another index m larger than an epsilon into the property of being Cauchy here. So I can apply Cauchy with n equal to nk. And if you put these two things together, you see that xm minus L is less than xnk minus xm plus L minus xnk, where the first guy is less than epsilon by the Cauchy property, and the second guy is less than epsilon since the subsequence was converging. So this is less than 2 epsilon, and for which values have you proved that? For every m larger than an epsilon. And that's the definition of xn converging to L. Okay. That is, for every epsilon positive, xn is ultimately 2 epsilon close, which is the same as being epsilon close to L. Okay, take a moment to think about this and tell me if you have questions. Even if you just have a point that right now is not so clear, without thinking too much about it, just put the point.
So step one was just to prove that Cauchy implies bounded.
Yeah. And then I use that to find the convergent subsequence, which is easy, right? Like that's Bolzano Weierstrass theorem. But then I combine the being Cauchy with having the convergent subsequence to say that everything has to converge. And the way you should really think it, let me try to draw a picture here, okay? Just to understand this more graphically. Say that our sequence xn, these are not values in R. Imagine this as value in R2, in the plane. Okay? What it means? It means that I am picking up points, right? It's like I have a watch, and that each second I record the position of a particle. So this would be my sequence xn, right? So xn, it's here, it's there. So I kind of taking track of where my particle moves, right? This is how I understand the sequence in the plane. Now I have discovered that two things. I know that my sequence is Cauchy. It means that if I pick a value xn large enough, then after a while the oscillation will be epsilon. So all the values will just be in the neighborhood of this point. Okay? This means the oscillation goes to 0. But I'm not sure if I'm converging somewhere, right? You see what's the problem? Because maybe, okay, after this value, the oscillation is all here, but then can it really be that now I have an xm which is here? Not really, because all the values after that must sit in there, right? And the oscillation must become smaller and smaller. So you see, it's like I am trapped inside this little ball with a smaller and smaller oscillation, and then after that I am trapped inside this ball, and then it's kind of game of trapping, right? So this picture, in a sense, it's wrong. So let me, it's like, say that I fix an epsilon, and I know that for every m larger than this value, my oscillation is in there, right? So all the values of the sequence will happen inside this thing. Does it imply that I have a limit? Of course not. I could still oscillate between two guys, right? Without having a limit. But I am Cauchy, right? So I can tell you that, well, now let's consider epsilon over 2. At a certain point, the oscillation becomes smaller than epsilon over 2, isn't it? So it means that at a certain point, I will be able to choose one of these points, and the oscillation will be less than epsilon over 2. So it means that all these other points were finitely many, and I can forget about them, right? From now on, everything happens inside this ball of radius epsilon over 2, where, of course, yeah, all I know is that I live inside this epsilon over 2 of space, okay? But I am Cauchy, so I can do epsilon over 4, and I know that, well, everything after a while will be in the ball epsilon over 4 around this point. So all these crazy things that may hint to an oscillation are actually finitely many. So it's like they don't matter. Okay? And then from now on I live here. Okay? In this ball of radius epsilon over 4. Inside of which the picture repeats, right? Because now this is a ball epsilon over 4 where I know nothing but that I stay here forever. But there will be one of these points where after a while I don't move back by an epsilon over 8 for all the terms in the sequence. So these other guys were finitely many. So that's why you converge. You converge because, in a sense, each time you have less space to go around, to move around, because the oscillation is going to 0. So which means that somehow all you have to do is to find something that stays somewhere, that it's moving somewhere, and that's my subsequence there. So you see, my subsequence x and k has just the role of telling me how am I picking these kind of hooks, or these trapping points, that tells me that the things stay close to a limit value. That's it. And then the fact that I am oscillating little around this value is just being Cauchy. So think about this theorem. That's a really, really extremely important proof, okay? Because it really trains you to think geometrically about these objects, you see? Now I've drawn a picture in the plane, so I have more space, it's more geometrical, okay? But you can do the same picture in an interval, it's going to work as good in the line. Okay, let me give you an application, yeah.
So when we are proving out the theorems, we always make sure that the inequality we end up with is less than or equal to epsilon, 1 epsilon, but it's okay if we end up with 2 epsilon?
Yeah, as soon as you are ready to explain that ultimately to epsilon closed for every epsilon is the same as ultimately epsilon closed for every epsilon. Remember, it's 4, so being ultimately to epsilon closed does not imply that you are ultimately epsilon closed. Two different things. Because to epsilon is not epsilon, okay? It's twice it. But being a 2 epsilon closed for every epsilon, it's a different matter, because there is for every. So being ultimately 2 epsilon close to 1 is the same as being ultimately epsilon close to 1. So let me stress these. So the sequence being 2 epsilon close, ultimately epsilon close to 1 is, of course, does not imply that the sequence is ultimately epsilon close to 1. This for a given epsilon. So knowing this for a given epsilon, okay? For one value of epsilon doesn't tell you anything like that, right? And simply there are different numbers. But knowing that for every epsilon positive, you are able to show that you are ultimately to epsilon close, 1. Okay, now you see, I have much more information. I have a whole family of things. I'm telling you that no matter how epsilon is small, you will be ultimately 2 epsilon far away. But 2 epsilon now is really just a generic positive number because there is the forever in front of it. If you double a generic positive number, you end up having every positive number, right? So then these would be enough to say that for every epsilon, xn is ultimately epsilon close 1. Good. So now let me give you an application of this Cauchy theorem, so you see why it's interesting. So let's do the following here. So we start from x1 equal to 1, x2 equal to 2, and then we start making averages of the first of the previous 2 terms in our sequence. So we start from 1 and 2, right? 1, 2, then, so this is x1, this is x2, what is x3? x3 will be 1 alpha, because it's the average of the first 2. Then what is x4? x4 we'll see here, right? Because this will be the average of, 3 halves. Yeah, this will be the average of 3 halves and 2. So this will be 3 halves plus 2 over 2, which is like possibly 7 over 4. This will be x4. And then x5 will be the average of this guy and that guy. This will be x5. Then x6 will be the average of, I'm already lost. Okay, but you got the idea. So you compute averages, okay? So where is it going to converge? Sorry? 3 over 2? Then it moves. 1 half?
Somewhere between 1 and 2.
Yeah, exactly, right? So. So first of all, in order to do anything, you want to know that the limit exists, right? It's going to be helpful. So, how do you show that the limit exists? You check that this thing is Cauchy. All right? So, exactly. So we want to check. So to check that something is Cauchy, you just take xn minus xm. Let's say that n is less than m, and then we start taking triangular inequalities, right? So we have xn minus xn plus 1 plus xn plus 1 minus xn plus 2, and then here I have xm minus 1 minus xm, right? I apply the triangular inequality over and over again. Just understand what this is. So, what is the distance of 2 subsequent values, right? So what is xn minus xn minus 1, for example, for a generic n? So now, xn minus xn minus 1, if I just plug in, well, probably I want to do, looking at this formula, xn minus 1, yeah. And then we're going to apply it with shifted indexes so that you get lost. So this is going to be equal, if I plug the formula there, right, I subtract xn minus 1, I got an xn minus 2 minus xn minus 1 over 2. So you see, the distance between one term and the previous one is half the distance of the previous term and 2 terms before. So I have steps n minus 2, n minus 1, and n. So I've made 3 steps along my sequence. And the oscillation between n minus 1 and n minus 2 is half of, sorry, no.
The half should be on the other section.
Yeah, what am I saying? No, this is correct, right?
I don't know.
Yeah.
Yeah, the oscillation, okay, yeah. As you increase the index, the oscillation between one term and the subsequent has decreased over a factor of 1/2. So the new oscillation between n and n minus 1 has become half of what it was before.
Can we just say the derivative from that?
Yeah, I use the formula. Okay. So this means that if I go on, here I have xn minus 3 minus xn minus 2, 4. And if I go on a certain number of times, here I get something like x2 minus x1 over 2 to some power, which I may try to compute as n minus 2. Okay? Now, x2 minus x1 was 1, so this is 1 over 2 n minus 2. Okay? So that's how much is the oscillation. It's becoming, well, each time you're taking an average, right? So the starting average was 1, and essentially the sequence starts really with n equal to 3. So that's why. So this shows that if you do xn minus xn minus 1, this is equal to 1 over 2 to the n minus 2. So when I go back there to the situation where I have n less than m, and I compute xn minus xm, and I say that this is less than all these things here, so I have xm minus xm minus 1 plus xm minus 1 minus xm minus 2, and so on, right? Plus xn plus 1 minus xn. So I'm kind of writing the right-hand side, starting from the top and going the lowest indexes. Okay. This will be less than, so the first guy gives me, I have to apply this formula with n equal to m, but that's not too much. So m minus 2, right? Then I have the same thing with the index n minus 1. And then I go on with that, and then I have 1 over 2, and then I have, this is the index n plus 1 in the formula, so this is n plus 1 minus 2. So now it's not much important, I mean the numbers are correct, but if you're not getting them on the spot, you should be able easily to check them later. So, but the important thing is that what I'm telling you here is that xn minus xm is less than the sum, so it's less than 4 times the sum for k that goes from n plus 1 to m of 1 over 2 to the k, right? Because there is a 2 to the minus 2 everywhere, which is kind of a 4 multiplying everything, right? That's this minus 2 becomes the 4 over there. So I'm saying that 4 is 1 over 2 minus 2. Okay, and then what's left is you start counting from n plus 1 up to m, the geometric series. So that's the tail of the geometric series, right? This goes to 0. So, right, so this is less than, in this case it's less than 4, 1 minus the n plus 2 over 1 minus 1 half. That's the formula for the tail of the geometric series starting counting from n plus 1. You should know these things by heart, in my opinion. So if you have the sum of q to the k, and this goes from 0 to, I'm sorry, let's see. Yeah. And you go from n to infinity, okay? This is going to be, well, from m to some other number m, this is going to be less than, equal to q to the, less than, sorry, q to the n plus 1 over 1 minus q. This for every q less than 1. Well, let's say positive. Okay. So in particular, this goes to 0 as, So in particular, if n and m are larger than some n epsilon, right, then xn minus xm is less than some number. Now you got something like 8 over 2 to the power n epsilon plus 2, which I can make less than epsilon provided n epsilon is large enough. Okay, so my time is over unfortunately, but this shows you that this sequence is Cauchy, okay, and therefore it has a limit. There is a little additional argument that I hope to have the time to do that shows you how to compute it. So you should have a look to the example 3.5.6 in the book. Okay? So that's the first part of that argument, showing that it's Cauchy. So this thing has a limit, and now you can use that thing to, I mean, it's just a little additional argument to compute it, but it's easier.
Can we come get work right now?
Yeah, I'll be there in a moment.